So how does one precisely estimate the parameters? One approach to estimate graphical model is called moment matching. We start by assuming some choice of parameters for each node and edge. We first compute the induced moment by the graphical model using given choice of parameters and compare it with the empirically observed moments. If there is a mismatch, we slightly change the node and edge parameters to reduce the mismatch and repeat this process till we find a good match. That's it. Very simple. It is important to compute the moments induced by a graphical model in a tractable manner. A popular approach to do so is the belief propagation algorithm. I would suggest an interested listener to follow other parts of this course where graphical models are discussed in detail. So we have learned a probabilistic graphical model representation of user preferences. How can we use it for the purpose of recommendation? Consider a user. Suppose she has liked only Casablanca and that's all we know about her preferences. Now we want to recommend her movies from the remaining movies. Using graphical model, we can compute probability of her liking any other movie conditioned on the observation that she liked Casablanca. This is effectively assigning scores to each movie. We can use these scores to order movies and recommend them to her. That's it. Computing the score, as described earlier, requires computing distribution of each node subject to few observations from the entire graphical model. This is not a straightforward computational problem. A good computationally efficient algorithm for this is again the belief propagation. And this is exactly where graphical model representation comes to our rescue to allow for efficient computation. Now we shall discuss the second challenge we had outlined in the beginning: how to capture the temporal relationship between user preferences using graphical models. If you like movie Goodfellas, then a good recommendation algorithm, such as the probabilistic graphical model above, may suggest that you will like Godfather Part 1, Part 2, and Part 3. The question is, which one of these should be recommended first? As it is popularly believed, Godfather Part 2 was the best among all three parts, and I think I believe that too. And if this was captured by user preferences, then our system might end up recommending Part 2 as the movie to watch for a user who has not yet watched Godfather Part 1. And this does not make sense because if you have seen Godfather trilogy, then you know that watching them in order is crucial. To make such a distinction, the recommendation system has to take the temporal aspects into account. Most users who would have provided their preferences for Godfather movies would have watched Part 1 first and then Part 2 later. Therefore, if system utilized the temporal aspect of the user preferences, then such a problem would be solved. And that is what we will do next. Precisely, we shall describe how to use a hidden Markov model to solve this problem. We note that the so-called recursive neural network can be similarly utilized for this purpose as well. And it seems that companies like Spotify uses such an approach for recommending songs to its users. In a hidden Markov model, there is a notion of time. For each time instance, there is a hidden state and there is an observed state. The hidden state is assumed to take one of the finitely many values. The value of hidden state at time t plus 1 depends on the value of the hidden state at time t. The probabilistic relationship between consecutive hidden state is homogeneous across time. In this sense, the evolution of hidden state can be viewed as a Markov chain, and this is why it is called the hidden Markov model. Now, hidden states are not observed. Well, that is the reason why they are called hidden. Each time, depending on the value of hidden state, an observation is made. In our movie example, an observation would correspond to the movie preference of a user. For example, suppose a user has expressed the first preference as she liked Goodfellas and the second preference that she disliked Iron Man. Then the observed state at time 1 correspond to she liking Goodfellas. The observed state at time 2 correspond to she disliking Iron Man. In a nutshell, each user's preferences over time provide assignment to observed state of the hidden Markov model. Different user preferences are of different length, and hence we have observation of a hidden Markov model of different length depending upon each user. The goal is to learn the probabilistic relationship describing the evolution of hidden states, as well as the probabilistic relationship between the observed state and the hidden state at any given time. A popular approach to learn this relationship is known as the Baum-Welch algorithm. An interested listener will be able to find the precise algorithm description in other parts of the course. Now we shall discuss how to use such a hidden Markov model for recommendation to a given user. As before, suppose a user has expressed liking for Goodfellas and disliking for Iron Man. Then we know that the observed state at time 1 is Goodfellas is liked, observed state at time 2 is Iron Man disliked. Given this, using the learned hidden Markov model, we can compute the likelihood of any given model and liking being observed as a state at time 3. This provides score for each of the movie for which user has not provided her preferences. We can use this score to provide recommendations. If the data is rich enough and algorithms have done their job right, then in the example above, it may suggest a higher score for Godfather Part 1 rather than for Godfather Part 2, even though at population level, Godfather Part 2 might be liked more. That is, the recommendation system would have worked well by understanding the importance of order in which sequels should be watched. In summary, recommendation system based on view of matrix completion have two major limitations. One, that do not capture complex user preference relationship. Two, that do not capture temporal aspects. Graphical model can help us address these limitations in computationally efficient manner. We can use pairwise probabilistic graphical model to capture more intricate relationship. We can use hidden Markov model to capture the temporal aspects of user preferences. The use of neural network is very similar to the way we describe the use of graphical models today.